Dear students, today we'll discuss about colloidal solution. What is colloidal solution? What are different types of colloidal solution? Preparation of colloidal solution. Properties of colloidal solution. So let's start with colloidal solution. So we have a particular term which is known as colloidal solution. So first of all, to begin with, colloidal solution is a heterogeneous mixture in which one substance called dispersed phase is dissolved or dispersed in another substance called dispersion medium. So we have a heterogeneous mixture of two components. One is known as dispersed phase, the other one is known as dispersion medium. Dispersion medium is equivalent to the solvent in normal or general solution chemistry, whereas the dispersed phase is like solute which is present in lesser quantity. So this colloidal solution is not a particular state or particular class of substance, but is a state of matter like solid, liquid, gas. What we mean to say is these colloidal state or colloidal solution can be from any physical state like solid, liquid or gas. These physical states can be converted into colloidal solution by physical means or by chemical means. So this colloidal state does not represent any particular subclass of substance, but is a state of substance like solid, liquid, gas, which can be converted into the colloidal state or colloidal solution. So we have this colloidal solution. The basic feature of this colloidal solution is the size of the colloidal particles is ranging from 1 nanometer to 10 nanometer. If the diameter of the particles of this solution ranges from 1 nanometer to 10 nanometer or 100 nanometer, then those solutions are known as colloidal solutions. So we have this colloidal solution. So first thing is, this colloidal solution is heterogeneous mixture which consists of two components. One is known as dispersed phase, the other one is known as dispersion medium. This is the one which is present in larger quantity. Dispersed phase, this is the one present in lesser quantity. So the heterogeneous mixture of dispersed phase dispersed in another substance known as dispersion medium. This is what we call as colloidal solution. For this colloidal solution, the size of particles or the diameter of particles ranges from 1 to 100 nanometer. So this is the size of particles. If the size of particles ranges between greater than 1 nanometer but less than 100 nanometer, then these particles forms a solution which is known as colloidal solution. So if the question arises, if the size of particle is less than 1 nanometer, or if the size of particle is greater than 100 nanometer, then what is this? If the size of particle is less than 1 nanometer, then those solutions are known as true solutions. Whereas if the size of particle is greater than 100 nanometer, then those solutions are known as suspension. So we have three categories of solution. So let's see the difference between the three. So we have pure solution, we have colloidal solution, we have suspension. So these are three categories of solution. So the first one is particle size. For true solution, the diameter of size is less than 1 nanometer or less than 10 angstrom. So for a true solution, size of particle is less than 1 nanometer or less than 10 angstrom. For colloidal solution, the particle size is greater than 1 nanometer but less than 100 nanometer. So the size of particle is greater than 1 nanometer but less than 100 nanometer, or we can say this is greater than 10 angstrom but less than 1000 angstrom. This forms colloidal solution. But if the size of the particle is greater than 100 nanometer or 1000 angstrom, then this forms suspension. So this is first the size of difference between these three types of solution: three solution, colloidal solution, and the suspension. Second difference or properties concerning these three types of solution is visibility of particles. Now, in case of true solution, the particle size being less than 1 nanometer, this is not visible to naked eyes or cannot be observed with microscope. Whereas the size of colloidal particle being greater than 1 but less than 1000 angstrom, so this not visible to naked eyes but visible to ultra microscope. These particles cannot be observed with naked eyes, but they can be easily identified or observed by use of ultra microscope. Suspension, these are visible, the particles are visible to naked eyes. Yes, we can easily identify the particles with our naked eyes. So this forms suspension. Third difference between these three is filtrability. The size of particles in true solution being very small, that is less than 1 nanometer, this cannot be filtered by use of filter paper even by ultrafiltration, because the pore size of filter paper is much better than the size of true solution. Cannot be filtered. Whereas in case of colloidal solution, the particle size is less than the pore size of normal filter paper. That means these colloidal particles cannot be filtered by normal filter paper, but they can be filtered by ultra filter paper. Cannot be filtered by normal filter paper, but by ultra filter paper. That means we can impregnate these normal filter paper with some other substance, by use of which the pore size can be reduced. If the pore size can be reduced, then the particles of colloidal solution cannot pass through the filter paper. If they cannot pass through the filter paper, then this can be easily filtered by this ultra filter paper, but not by the normal filter paper. Whereas the size of suspension particles being very large, they can be easily filtered by normal filter paper. Easily filtered by normal filter paper. So we have this true solution, colloidal solution, suspension. So basically look at this, the particle size are different. True solution, particles are not observable with naked eyes even by ultramicroscope, whereas colloidal particles cannot be observed with naked eyes, but they can be observed by ultramicroscope. Suspension, they can be easily observed with naked eyes. Filterable, cannot be filtered, can be filtered by ultrafilter paper, can be easily filtered with normal filter paper. Fourth, this settling property. Settling property of these three different types of solution. True solution, the particles does not settle on standing. Does not settle on standing. That means if we keep on this true solution for a longer period of time, then the particles of this true solution will not settle down. That means the solution will remain as a true solution. Colloidal solution, again the particles do not settle down on standing, but in case of suspension, particles settle down on standing. So if you keep on standing this solution, after few means on after certain time, the particles will settle down. Next, this true solution is a homogeneous mixture, whereas colloidal solution is heterogeneous. Suspension is also heterogeneous. So we have this homogeneous mixture, we have heterogeneous mixture, we have heterogeneous mixture. So these are the basic difference between these three different types of solutions. These two solutions are transparent, whereas the particles of colloidal solution these are translucent, but the suspension these are totally opaque. That means if you pass a beam of light, the solution containing two solutions, the path of light cannot be observed, means we are getting a clear solution. Whereas in case of colloidal solution, if you pass a beam of light, the direction of movement of light will be observed by this colloidal solution due to scattering of light by the particles of colloidal solution. Whereas in case of such as suspension, if you pass a beam of light, the path traveled by this light will not be observed. That means this will totally cut off the path of light. So these are basic difference between these three different types of solutions. So now basically you are focusing on this colloidal solution. So all this is based on this size of particle. So this is the basic difference between these two. Once we have a knowledge of these two solutions, colloidal solution and suspension, now let's move on to the types of colloidal solution. Types of colloidal solution. So first, categorization of this colloidal solution based on the physical state of dispersed phase and dispersion medium. Based on the physical state of dispersed phase and dispersion medium, we can classify the colloidal solution into different forms. So we have dispersed phase, dispersion medium, and name of colloidal solution. So we have to look at this. Dispersed phase is solid, dispersion medium is also solid. That means solid, dispersion, solid. These are known as solid sols. We have solid, dissolvent, liquid. So dispersed phase is solid, dispersion medium is liquid. So if solid is dispersed in liquid, these colloidal solutions are known as simply sols. Third, if solid is dispersed in gas, then these types of colloidal solution are known as aerosols. So we have looked at this: solids, dissolving, solid, liquid, and gas. Next we have liquid, dispersion, solid. So we have liquid, dispersion, solid. These are known as gel. We have liquid, dissolvent, liquid. These are known as emulsion. We have liquid, dissolvent, gas. These are again known as aerosols. We have gas, dissolving, solid. These are known as solid sols. Then we have gas, dissolving, liquid. These are known as So these are the different categories of colloidal solutions based on the physical state of dispersed phase and dispersion medium. Whereas the last one, that is gas in gas, this is not a colloidal solution. So gas dissolved in gas always forms a homogeneous mixture. So this cannot form a heterogeneous mixture, whereas look at this colloidal solution is heterogeneous mixture, but gas dissolved in gas is always a homogeneous mixture. So this cannot form a colloidal solution. So these are the 8 different categories of colloidal solution based on the physical state of the dispersed phase and dispersion medium. Now sometimes these salts are given specific name based on the dispersion medium. So if the dispersion medium is water, then the salt is known as hydrosol. So if we have a colloidal solution prepared in water taking as a dispersion medium, then these types of colloidal solutions are generally given as hydrosols. If the dispersion medium is alcohol, then colloidal solution is known as alcosols. If the dispersion medium is benzene, then these are known as benzesols. So depending on the dispersion medium when used, specific names are given. If the dispersion medium is air, then colloidal solutions are known as aerosols. So these terms are given for specific dispersion medium. Otherwise, if the physical states are clearly mentioned, then we can classify this colloidal solution into 8 different categories which are given as. So this is first classification based on the physical state of the dispersed phase and the dispersion medium. Now coming to second classification, that is based on the nature of interaction between the dispersed phase and the dispersion medium. Based on nature of interaction between dispersed phase and the dispersion medium. So based on this nature of interaction between dispersed phase and dispersion medium, we can classify this colloidal solution into 2 different. One is known as lyophilic solution, colloidal solution. The other one is known as lyophobic. So we have 2 class of colloidal solution, lyophilic and the lyophobic. Now this lyophilic, as the name suggests, these are known as solvent attracting or liquid attracting. That means if there is a greater attractive force between the dispersed phase and dispersion medium, then those types of colloidal solutions are known as lyophilic. Whereas in case of lyophobic, as the name says, phobia, that means the interaction between the 2 components is a very weak, or we can say there is a repulsive force between dispersed phase and dispersion medium. So these are known as liquid heating. So One we have lyophilic, liquid attracting or liquid loving. The other one's lyophobic or liquid hating. Now, these lyophilic salts or lyophilic colloidal solutions can be easily prepared by mixing the two components, that is dispersion phase and the dispersion medium. If the two components are mixed, they can easily be converted into colloidal solution. So this can be easily prepared by simply mixing the two. So without any external help, we can easily mix the dispersion medium along with disperse phase, and we can convert this into colloidal solution. So those type of solutions which can be easily prepared by mixing disperse phase in dispersion medium are known as lyophilic salt, whereas these second category, that is lyophobic colloidal solutions, cannot be easily prepared simply by mixing the two, but by special methods. Because to prepare this lyophobic salt, we need to take the help of some other stabilizers. Without the help of those stabilizing agents, the lyophobic salts cannot be prepared. So they cannot be prepared by simply mixing the two, but by special means. So only by special means we can prepare this lyophobic salt. So now coming to next. Now since these lyophilic salts can be easily prepared by this mixing of the two components. Now if by any means if we separate this dispersed phase from dispersion medium, means we are separating dispersed phase from dispersion medium, then the two can be simply combined to give you this lyophilic salt. So you mix the two, we get a lyophilic solution. You separate the two, after separation again mix the two, then you can get this lyophilic salt again. So we say this is reversible in nature. That means lyophilic salts can be easily prepared by mixing the two. We can also separate. After separation, we can again combine the two to give you the lyophilic salt. Whereas lyophobic salt is a irreversible, meaning these lyophobic salts are prepared by specific means. Means this cannot be simply prepared by mixing dispersed phase in dispersion medium. Now we have a lyophobic salt. Now we separate the components of lyophobic salt, dispersed phase and dispersion medium. After this separation, they are mixed together again. By simply mixing, the lyophobic salt cannot be obtained again. That means the process of mixing of the two components, separation, again and remixing cannot obtain this lyophobic salt. So we say these are irreversible in nature. Lyophilic salts, the viscosity of lyophilic salts are greater than that of medium. Means we have this dispersion medium, we take the viscosity of dispersion medium. Now to this we add dispersed phase, we obtain lyophilic salt. Now we measure the viscosity of lyophilic salt. So when we compare the viscosity of lyophilic salt with that of the dispersion medium, the viscosity of the lyophilic salt is always greater than that of the dispersion medium. Whereas in case of this lyophobic salt, the viscosities are almost same. surface tension. Now, when we compare the surface tension of this lyophilic sol with that of dispersion medium, the surface tension of these lyophilic sol is less than that of medium. So the surface tension of this lyophilic sol is less than that of the dispersion medium, whereas in case of lyophobic sol, these are almost same. So both the viscosity and the surface tension of these lyophobic sols are approximately same as that of the dispersion medium, whereas in case of lyophilic sol, the viscosity is greater than the medium, whereas surface tension is less than that of medium. Lyophilic sols is because there is an attractive force between these two. These are stable, whereas lyophobic sols, these are unstable. Means when we compare the stability of this lyophilic and lyophilic sols are more stable compared to that of lyophobic sols. Lyophilic sols or colloidal solution, these are usually formed by organic compounds like starch, protein, gum, gelatins, whereas these lyophobic colloidal solution, these are formed by inorganic like metals, their sulfides, etc. So this is the second classification of colloidal solution based on the nature of interaction between the dispersed phase and dispersion medium. Now coming to third classification of colloidal solution. Third classification, that is based on nature of dispersed phase. Based on the nature of dispersed phase, we can also classify this colloidal solution into different forms. We have multimolecular colloidal solution. So the first type of colloidal solution based on the nature of dispersed phase, that is known as multimolecular. So as the name suggests, look at this, we have many. So in this case, what we have is we have atoms or small molecules. We have large number of atoms or small molecules of a given substance aggregates to form a solution in which the particle size is in between 1 nanometer to 100 nanometer. That means initially we have very small particles, and that is atoms or small molecules of a given substance. This collision undergoes aggregation. When these aggregates, larger size particles are formed, which dimension falls in between 1 nanometer to 100 nanometer. So these types of colloidal solution formed by atoms or small molecules is known as multimolecular colloidal solution. So these multimolecular colloidal solutions, we have examples like colloidal solutions of gold, silver, platinum, sulfur, etc. So in this we have molecules of sulfur aggregating to form colloidal size. We have atoms of gold, silver, platinum aggregates to form bigger particles whose solid particle size falls in colloidal range. So we have this multi-molecular. Second is macromolecular. Macromolecular colloidal solution. So as the name suggests, macro stands for large. So we have in this second category, we have larger size particles having high molecular mass or large molecular mass. So larger size particles having large molecular mass, these aggregates to form colloidal solution. In the first case, we have atoms and very small molecules aggregates to form colloidal solution. Whereas in the second case, the dispersed phase that we are taking, which is to be dissolved or dispersed in a dispersion medium, are already a large particle. So large particle means the molecular mass of the particle should also be large. So large particles with large molecular mass, if they are dispersed and this forms colloidal solution, then that type of colloidal solution is classified as macromolecular colloidal solution. And these macromolecular solutions, colloidal solutions, are formed by proteins, starch, gelatin, etc. So already we have a proteins. The molecule proteins are macromolecules or polymers. Starch, gelatin, these are polymers. So we have a large size particle. Obviously, the molecular mass is also large. So these particles forms colloidal solution. So this comes under macromolecular colloidal solution. The third category is associated molecules. Third category is associated molecules. So we have a specific electrolytes. We have certain electrolytes. These electrolytes at very low concentration behaves like a strong electrolyte. So we have a substance. We have a certain substance at very low concentration. They behave as if like strong electrolyte. But at higher concentration, these does not show electrolytic behavior, but this shows colloidal property. So we have a substance which at very low concentration, this behaves as a strong electrolyte. But if the concentration is increased and after certain level, the solution behaves like colloidal solution. So those type of colloidal solutions are known as associated or simply known as micellary. So we have look at this. At this low concentration, they behave like strong electrolyte. But at a higher concentration, they behave like colloidal solution. So these types of colloidal solution formed by these particular substances are known as associated colloidal solution, or simply we say micellary. Substance is same, but we are changing the concentration. Low concentration, normally strong electrolyte, but at a higher concentration, they forms colloidal solution. So now look at this. For this micellary formation of associated colloidal solution, some concentration limit must be there. So that concentration limit is known as critical micelle concentration, that is CMC. So we are defining this critical micelle concentration. For this micelle formation or associated colloidal solution formation, the colloidal solution formation takes place only above a certain minimum concentration. So that minimum concentration below which micelle formation does not take place, or above which the micelle formation takes place, that concentration is known as critical micelle concentration. So for this micelle formation, the minimum concentration required is CMC. If this is less than this CMC, no formation of micelle takes place, but only above this critical micelle concentration, formation of micelle takes place. So critical micelle concentration is the minimum concentration above which micelle formation takes place. Now, for this micelle formation, again some temperature condition is required. There is a certain minimum temperature below which this micelle formation does not take place, or this micelle formation takes place only above some minimum temperature. So that minimum temperature above which this micelle formation takes place, which is known as trough temperature. So this trough temperature is defined as the temperature above which the micelle formation takes place. So this is conditions required for micelle formation. Concentration should be above this minimum value, that is critical micelle concentration, and the temperature should be above this trough temperature. If this condition is satisfied, then this micelle formation takes place, resulting in the formation of a colloidal solution. If not, then this substance will not form micelle. Now, basically, this substance above this CMC and above this trough temperature forms micelle. So, what is the mechanism of micelle formation, or how this micelle formation takes place? Let's see. Micelle formation. Now, to explain the micelle formation, we take the help of soaps and detergent. Soaps and detergent. Normally, this soap is defined as sodium or potassium salt of long chain fatty acids. Sodium or potassium salt of long chain fatty acids are classified as soaps. So long chain fatty acids means we have a large number of carbon atoms like C17, stearate, palmitate, laureate. So whose can be generally that is RC double bond O minus. Either we have this sodium salt or potassium salt. This is acid. These are, that is, long hydrocarbon chain. So we have soaps and detergent. This is salt of long chain fatty acid, sodium or potassium salt. So R is a long hydrocarbon chain. So these can be represented as these long hydrocarbon chain. These are, this we have pure hydrocarbon. So hydrocarbons are hydrophobic. So this is hydrophobic, and this hydrophobic part, this is also known as tail And look at it, this is salt. Salt is soluble in water. This soluble part, this is known as polar, and this is known as head, and this polar part is hydrophilic. That means these soaps and detergent contains two parts, hydrophilic as well as hydrophobic part. Hydrophobic part is what not soluble in water. These are known as tail, and the polar head, this is soluble in water. This is known as hydrophilic. So we have looked at this. This is head, and this is polar. This is hydrophilic. This part, this is tail, that is hydrocarbon part, that is non-polar, and this is hydrophobic. So we have both hydrophobic and hydrophilic. Now, when this particles of soap, that is sodium or potassium salt of long chain fatty acids, is dissolved in water, these ionized to give you carboxylate anion and sodium salt or potassium salt. And the carboxylate anion contains water soluble head and water insoluble tail. When these are dissolved in water at certain concentration, now look at this, we have this hydrophobic and hydrophilic. When this is dissolved in water, this head being hydrophilic will try to remain in water, whereas the tail, that is non-polar end or hydrophobic part, being not soluble in water, will try to remain away from water. That is, suppose we have a container. This is water. We have added soft molecules. Then hydrophobic part will remain away from water, whereas hydrophilic part will remain inside the bulk. This is the general normal orientation of this hydrophobic and hydrophilic. Hydrophilic part will remain in the bulk. Hydrophobic part will remain away from the bulk, and this will remain at the surface. Now we dissolve these salt molecules in water. When this is dissolved in water, the hydrophilic part will remain inside the bulk, and the hydrophobic part will remain away from the bulk, because this being hydrophobic will try to remain away from water. At certain concentration known as CMC, these hydrophilic part forms a spherical, and that remains inside the bulk, and the hydrophobic part is pointed inside the sphere. That particular spherical formation is what we call as micelle. So when these are dissolved in large quantity above certain concentration known as CMC, the hydrophilic part, that is remains in the bulk, and the hydrophobic part will point it away from the bulk and remains at the surface. Now this results in the formation of something like spherical shape. This spherical, now this is hydrocarbon tail, which is pointing away from the bulk, and this is inside the sphere, center of the sphere, and this hydrophilic part being water soluble remains in the bulk, resulting in formation of this spherical. So this spherical formation is what we call as micelle. So basically this is only possible because of the presence of lyophobic and lyophilic. Lyophilic part remains in the bulk of the solution, whereas lyophobic part remains away from the solvent, resulting in the formation of a spherical structure which is known as micelle. Now this micelle formation is responsible for the cleansing action of soaps and detergents. So we have soaps and detergent which is used for cleaning the dirt, and during the process these soap molecules and detergent molecules forms micelle. So what is happening is the dirt substance is basically fats or organic compound, oil or fats which is basically organic compound. So when the piece of cloth containing dirt is dissolved in a soap solution or detergent solution, the particles of soap forms micelle around the dirt particle. That means the hydrocarbon, look at it, if suppose this is the dirt being organic compound, oil or fat, the hydrocarbon tail will dissolve in this dirt and the hydrophilic part will remain in water, resulting in the formation of micelle. So we have a micelle forming around this dirt particle. The dirt particle is organic compound which is fat or oil. Now if you look at this micelle formation, this head we have negative negative. So there is a large enormous repulsion between this negatively charged heads. As a result of this repulsion between these negatively charged heads, this micelle breaks into smaller fragments. Why? Because of this repulsion. Because of repulsion between like charges, that is negative negative, we have a large repulsive force. This repulsive force breaks this larger dirt into smaller fragments, resulting in the formation of emulsion. So during agitation or rinsing with water, mechanical stirring, this tendency for breaking of this micelle into smaller fragments, resulting in the formation of emulsion increases. Once this emulsion is formed, it forms emulsion with water, and after rinsing with water, normally look at this, here is the controlling authority, is the head directs, okay, you have to move and one has to move. If this says you have to sleep, one has to sleep. If this says okay, you have to take rest, this will take rest. So during rinsing with water, the head goes with water. As the head goes with water, the dirt particle is taken along with this head, because this dirt particle is associated or mixed with this tail. So this is how dirt particle is being cleansed by soaps and detergents. So after this classification of colloidal solution, now we'll go to preparation of colloidal solution. Preparation of colloidal solution. What are different methods by which this colloidal solution can be prepared? So the first method is British arc method. British arc method. Basically, this method is used for metal salts like gold, silver, platinum, etc. So, in this British arc method, what we are doing is we take this metal for which colloidal solution is to be prepared as electrodes. So, both cathode and anode is of same metal, and these electrodes is dipped in a dispersion medium in which colloidal solution is to be prepared. So we have electrodes and these electrodes are the metal for which colloidal solution is to be prepared, and these are dipped in a suitable dispersion medium. Now, electric field is applied or potential is applied across this electrode. As the potential is applied across these electrodes, which are dipped in a suitable dispersion medium, intense heat is generated. The intense heat generated during passing of this voltage results in this metal is vaporized. So we have metal rod taking as electrode, dissolved in a dipped in a dispersion medium, and voltage is passed through. When the voltage is passed through these electrodes, intense heat is generated, and this heat vaporizes some of the metals. So during this vaporization of solid metals into vapor, due to the intense heat from this voltage, now these are dipped in a suitable medium. These vapors are again condensed. As a result of this, the particles are converted into colloidal solution. So first thing is, we have taken a container with suitable dispersion medium and metal rod for which we require to prepare colloidal solution taken as electrode. Now voltage is passed through this, heat generated, vaporized some of the metals, and these metals, vaporized metals, is again condensed by dispersion medium, resulting in the formation of colloidal solution. So this is what is Briggs arc method, basically for this metal source. The second method is peptidation. Peptidation. So peptidation means conversion of precipitate into colloidal solution. So we have a freshly prepared precipitate. This freshly prepared precipitate is to be converted into colloidal solution by use of an agent known as peptiding agent. So that means we have a freshly precipitate. This freshly precipitate is mixed with another agent known as peptiding agent, which has a conversion of this precipitate into colloidal solution and is second with a suitable medium. So precipitate, peptiding agent, medium, shaking is converted into colloidal solution. Now, what is the cause of this peptidation? How this precipitate is to be converted into colloidal solution? By use of this special agent, which is known as peptiding agent. Now, these peptiding agents are normally electrolytes in which one of the ion is common to the ion present in precipitate. So peptiding agent is electrolyte in which one of the ion is common to the ion present in precipitate. Now, when this precipitate mixed with peptiding agent and colloidal solution is taken, the ion which is common to the ion present in precipitate gets absorbed on the surface of precipitate. That is preferential absorption of ions on the surface of precipitate. If the ions are absorbed on the surface of precipitate, same ions will be absorbed around this precipitate. So we have the same ion, charges are same. So because of the same charges, there is an enormous repulsion, and because of this repulsion, the bigger particles are broken into smaller fragments whose size forms a colloidal solution. So the cause of peptidation is selective or preferential absorption of ions on the surface of precipitate, resulting into enormous repulsive force, which results in breaking of the bigger precipitates into smaller fragments, resulting in colloidal solution. So the cause of peptidation is preferential adsorption of ions on the surface of precipitate. Let me give you some examples here. Now we have, suppose, look at this AgI. This is solid precipitate. Now this AgI is mixed with silver nitrate aqueous solution and shaken. Now look at this, we have Ag common. So these AgI, on the surface we have silver ion antidote. And this is converted into colloidal solution. So AgI shaken with silver nitrate, this gives you AgI colloidal solution. This is due to adsorption of AgI on the surface of AgI. Same way, if this is shaken with potassium iodide, now look at this, we have I common. So I minus ion adsorbs on the surface of silver iodide, and this is converted into colloidal solution. So silver iodide can be converted into this colloidal solution either by shaking with aqueous silver nitrate or by aqueous potassium iodide. And this is also the responsible for the stability of the colloidal solution. Means every colloidal solution is a charged particle. They have either positively charged or negatively charged, which is due to selective or the preferential adsorption of ions common to the ions present in the colloidal solution, colloids. Now because of this, look at this, there's a repulsive force, so all the colloidal particles of area will have same charge, that is either negatively polarized or positively polarized. So these same charges cannot come across. So there's also a repulsive force. Because of this constant repulsive force, the molecules are in constant motion and they cannot be settled down. As they cannot settle down, this results in the formation of the colloidal solution. So peptidation, selective preferential adsorption, which is also responsible for the non-settling property or the stability of the colloidal solution. This is one of the methods by which we can prepare colloidal solution. Another method is chemical method, means by use of chemical reaction. So under this chemical reaction we have a different method by oxidation. By oxidation method, so look at this, we have sulfur dioxide plus H2S. This gives you sulfur salt plus H2. Look at this. This was sulfide ion. Now sulfide ion is oxidized to 0 by the sulfur dioxide. So this is how sulfur salt is prepared from hydrogen sulfide and sulfur dioxide. We can also take this H2S. Either this is taken with bromine water or nitric acid. In both the case, this is converted into sulfur salt. So minus 2 is oxidized to 0. This is oxidation method. If you have oxidation method, then there is a possibility of reduction. So by reduction, look at this. We have, look at this, auric chloride heated with zinc chloride. When gold in plus 3 is converted into 0 and it is converted into colloidal solution plus SnCl4. So this plus 2 is oxidized to plus 4 and gold is reduced to. In the same way we can take this PgCl4 plus SnCl2. So platinum plus 4, 0 plus SnCl4. So this is reduction method. Then there is also double decomposition method. Double decomposition method. We have this example like AH2SE, arsenic sulfide with H2O, arsenic oxide with, when this undergoes double decomposition to give you AH2S3 salt plus H2O. So there is exchange of anion, oxygen and sulfur. Initially oxygen was attached to arsenic, now this is attached to hydrogen. Sulfur which was attached to hydrogen, now this is attached to arsenic. So this is double decomposition. So these are the chemical methods by which we can prepare colloidal solution. After this preparation of colloidal solution, let's go to purification of colloidal solution. How this colloidal solution can be purified. Purification of colloidal solution. The first method for purification of colloidal solution is dialysis. So dialysis is the method by which we can remove the impurities from the particles of colloidal solution. Now, this process, dialysis, is based on the mechanism that all the impurities, that is electrolytes, present in the colloidal solution can pass through a certain specific membrane, whereas the particles of colloidal solution cannot pass through that membrane. So this is something like kidney dialysis. Kidney functions the dialysis or the purification of blood, which is a colloidal solution from the impurities. So one of the methods is dialysis. That means we take this impure colloidal solution containing impurities taken in a specifically designed membrane, and this membrane containing impure colloidal solution is placed in a pure water. Now the impurities can easily move through this membrane. So when this is placed in aqueous solution or pure water, impurities will move out from this to the pure solvent. Only the pure colloidal particles will remain inside the bag that is made of a specially designed membrane. So this is how we carry out dialysis. There is now normally dialysis process is a very slow process, because look at this, we take a bag which is made of this specially designed membrane. Inside this bag we place impure colloidal solution, which is again then dipped in a pure solvent. So impurities moves up from inside of this bag to the solvent side. After certain time, again this water should be thrown out, take another pure water, again we have to place. This very small and long time taking process. So to increase the process, this is carried out in electrodialysis. That means dialysis by use of electrodes. So means the same process taken, but we have deep electrodes. When we dip electrodes pass through electric field, the process becomes fast. That is electro dialysis. Then we have ultra filtration. Ultrafiltration, the pore size of normal filter paper being very large, the colloidal particles can easily pass through, so we cannot take this normal filter paper for purification of colloidal solution. But this normal filter paper can be, the pore size of normal filter paper can be decreased when this is impregnated with cellulose nitrate solution. So when this normal filter paper is being in a cellulose nitrate solution, the pore size is decreased. As the pore size is decreased, the colloidal particles cannot pass through this pore size, only the impure electrolytes can pass through. So by use of specially designed filter paper, we can purify this colloidal solution. That specially designed paper is ultra filter paper. Next method for purification of this colloidal solution is centrifugation, or simply ultracentrifugation. So centrifugation is a small device which can be rotated in varying speeds. Means this is to be connected to electrical circuit, and we can rotate the device by various speed. Now the colloidal solution which is to be purified is taken in a small test tube, and this is placed inside the centrifuge machine and in a tilted position, and this is rotated in varying speed. On rotation, the colloidal particles being heavier in size, these settle down at the bottom of the glass tube, and the impurities remains at the top. So after this, we remove the test tube for the impurities, that is the medium, and we take this solid as a purified colloidal solution, which is again mixed with a dispersion medium, shaken, and is to be converted into colloidal solution. So these are the methods by which we can purify colloidal solution. After this purification of colloidal solution, let's go to the property of colloidal solution. Properties of colloidal solution. We'll discuss some specific properties of colloidal solution. First property is Brownian motion. Brownian motion. So when we observe the colloidal solution by use of ultra microscope, the particles of colloidal solution were found to move in an irregular zigzag way. This irregular zigzag movement of particles of colloidal solution is known as Brownian motion. So because this was the first for the first time observed by Brownian, so in honor of the scientist, this is given as Brownian motion. So this is zigzag motion. This irregular zigzag motion of the particles of colloidal solution is known as Brownian motion. Now, what is the cause of this Brownian motion? The cause of this Brownian motion is unequal impact bombardment of the particles of colloidal solution by the dispersion medium. So we have a Brownian motion, that is zigzag or irregular movement of particles of colloidal solution. This zigzag motion is due to unbalanced or unbalanced bombardment of the particles of colloidal solution by the particles of dispersion medium results in an irregular decay motion which is known as Brownian motion. So I have given you what is the cause of decay motion, Brownian motion, that is unbalanced or unequal bombardment of the particles of colloidal solution by the particles of dispersion medium. And this Brownian motion is also responsible for the stability of the colloidal solution, because the particles are moving continuously due to this unequal impact or bombardment of particles. This continuous zigzag motion does not allow the molecules to come closer and stick together and settle down. So this is also responsible for the stabilization of the colloidal solution. Next is Tyndall effect. This is also known as optical property. So we have a colloidal solution. Now pass a beam of light. When a beam of light is passed through a colloidal solution, the path traveled by this light is clearly visible, and this is what we call as Tyndall effect. That means when a beam of light is passed through a colloidal solution, the path traveled by light is clearly visible, and this effect is what we call as Tyndall effect. And the cause of this Tyndall effect is scattering of light by the particles of colloidal solution. So when we strike this solution, colloidal solution, with a beam of light, the particles of this colloidal solution present in this solution scatters the light. Due to the scattering of light by the particles of colloidal solution, the path traveled by the light through this solution becomes clearly visible. That effect is what we call as Tyndall effect. Now for this Tyndall effect, the requirement is the size of particle and the wavelength of the light used should be approximately same. If there is a large difference, then scattering will not be observed. So for this effective scattering, the size of particle and the wavelength of light should be approximately same. Size of particle should be approximately same instead of wavelength of light used. The second condition required for this Tyndall effect is the refractive index of dispersed phase and dispersion medium should be differed by large value. So large difference in the refractive index of dispersed phase and dispersion medium. So there must be a large difference in the refractive index of dispersed phase and dispersion medium, and the size of particles and the wavelength of light should be used for this to be approximately same. If this condition is then the path of light travel can be clearly observed. This is known as Tyndall effect. Now this is due to scattering of light. Scattering of light is responsible for the Tyndall effect, that is optical property. So for this requirement is particle size and wavelength should be approximately same, or there should be large gap, whereas there must be a large difference between refractive index of dispersed phase and dispersion medium. Only then we can clearly observe this Tyndall effect. Whereas in case of Brownian motion, we have said that is unequal bombardment of the particles of colloidal solution by the particles of dispersion medium results in irregular zigzag motion, which is responsible for destabilization of colloidal solution. So this zigzag motion depends on two factors, that is viscosity. If the viscosity is large, then this zigzag motion will be less. So viscosity should be low. As the viscosity of the solution is less, this irregular zigzag motion should be more. So viscosity should be low for this Brownian motion to be effective. Second, temperature. If temperature is increased, this irregular or zigzag motion will also increase. So this is Brownian motion. This is Tyndall effect. Then we have electrical properties. Electrical properties. As we have mentioned earlier, the colloidal particles are normally charged, and if this is charged means either we have positively charged or we have negatively charged. The charge on all the colloidal particles in a given colloidal solution are same, and the cause of this charge, as we have mentioned earlier, this is due to selective or preferential absorption of an ion, which is the ion common to the ion already present in the colloidal solution. This selective absorption gives rise to charge. So we say we have colloidal particles which are charged. So how to prove that these colloidal particles are charged particles? For this we take the help of an experiment known as electrophoresis. Electrophoresis. That means in this we take a colloidal solution, and inside this colloidal solution, two electrodes are dipped. One is cathode, other one is anode, and potential is passed through. So when potential is passed through the electrodes dipped in a colloidal solution, these particles of this colloidal solution being positively charged or negatively charged, when potential is applied, the particles are moving either to the cathode or towards the anode. If there is no net migration of ions or the particles of colloidal solution, we simply say that there is no charge. If there is net migration of the particles of colloidal solution under the influence of electric field, then this only proves that the particles of colloidal solution are charged. If these are cation, then these are moving towards the cathode. If these are anion, then these are moving towards the anode. So the particles of colloidal solution, when passed through, when electric potential is applied to a colloidal solution through electrode, the particles are moving towards the cathode or towards the anode, just depending on the charge of the colloidal particles. This movement of particles of colloidal solution under the influence of applied field is known as electrophoresis. This electrophoresis proves the electrical properties. Okay, this is net migration of colloidal particles under the influence of applied field. If you have cations are moving towards cathode. If you have anions moving towards anode. So this net migration is One is electrophoresis, and this proves the charge on the colloidal particles. And the charge is because of preferential or selective adsorption, and which adsorption is the common ion. The ion should be common to the electron as well as the colloidal particles. So we have positively charged colloidal solution and negatively charged colloidal solution. So positively charged means we have looked at this metal hydroxides. Metal hydroxide salts are positively charged. That is, look at this. Fe2O3, we have Al2O3, we have Cr2O3. So metal hydroxide salts are positively charged. Whereas in case of negatively charged, we have metal salts like silver, gold, platinum, and their metal sulfides. Sulfide salts. So metal salts and sulfide salts are negatively charged, and metal hydroxide salts are positively charged. So these charges can be proved by this electrophoresis, and the cause of this charge on colloidal particle is because of preferential adsorption of ions common to the colloidal particle. This is electrical properties. Now we are saying that these are charged. Now if we have a charge, look at this. We have suppose look at this. Silver nitrate in potassium iodide. That means we take potassium iodide in large quantity, and to this we are adding small dose of silver nitrate. When this is dissolved, then we have silver iodide is formed. On the surface of this silver iodide, I minus are adsorbed. And this gives you negatively charged colloidal solution. So look at this. We take potassium iodide in container. To this we are adding silver nitrate. As silver comes in with contact with I minus, this is from silver iodide. Around this silver iodide, I minus from solution adsorbed and results in the formation of negatively polarized silver iodide salt. To reverse this case, we take potassium iodide in silver nitrate aqueous solution. The process is reversed. We take potassium silver nitrate in container. To this we are adding potassium iodide in small dose. As I minus comes in contact with silver, this forms silver iodide. But look at this, we have silver ion access. So on the surface of silver iodide we have this Ag plus adsorbed. So this becomes positively charged colloidal solution. So silver nitrate in Ki negatively charged. Potassium iodide in silver nitrate, that is positively charged. In the same way, look at this, we can take this FeCl3 in hot water. FeCl3 in hot water. This gives you ferric oxide. This is positively charged. Ferric ions adsorb on the surface of ferric oxide. But if the process is taken in this way, ferric chloride in sodium hydroxide. So when ferric chloride is dissolved in sodium hydroxide, this gives you ferric oxide. Now on the surface of this ferric oxide, look at this, we have OH minus N access. So this OH minus N adsorbs on the surface of ferric oxide, resulting in the formation of negatively charged colloidal solution. So there is preferential absorption. Now look at this. Suppose take this. We have this AgI. Now this is colloidal solution. Now either we take this Ag plus or I minus. So let's suppose on the surface of this AgI, I minus absorbs. So this is negatively polarized. Now solution also contains counter ions. So these particles of colloidal solution are polarized either due to addition of negative charge or due to addition of positive charge. But the solution also contains counter ion. So these charges on colloidal solution will attract counter ions from the solution. So suppose take this, the counter ion is K, so we have a K plus ion here. So the first layer, this is I minus getting adsorbed on the surface of colloidal particle. This is known as fixed layer, and the counter ion which is affected by this fixed layer, this is known as mobile layer. So we have a fixed layer. This is directly attached to the surface of colloidal by adsorption, that is fixed layer. Now this development of double charge. So we have a double charge, negative and positive. This is known as Helmholtz double layer. Development of charges between the fixed layer and mobile layer is known as Helmholtz double layer. So double layer is one is fixed layer which is directly adsorbed on the surface of colloidal particle, and the other layer is known as mobile layer which is the counter ion attracted by the fixed layer. Now look at this. This is electrical double layer which is known as Helmholtz layer. Now we have a negative or we have a positive. So there is a charge difference. Because of this charge difference, a potential is developed, and that potential developed across this double layer. Potential developed across this Helmholtz electrical double layer or simply double layer. This potential developed is known as zeta potential or electrokinetic potential. So zeta potential or electrokinetic potential is a potential difference developed in Helmholtz double layer, that is between the fixed layer and the mobile layer. This is what we call as zeta potential or electrokinetic potential. So every colloidal solution is having a charge due to preferential adsorption of ions common to the colloidal particle that gives rise to a fixed layer. So solution, the fixed layers attracts the counter ion from the solution, resulting in the formation of electrical double layer which is known as Helmholtz double layer. Due to the formation of this Helmholtz double layer, an electric potential is developed. That potential developed across this double layer is defined as zeta potential or electrokinetic potential. That is the electrical properties of colloidal solution. So next is coagulation or precipitation or coagulation of precipitation or flocculation. Coagulation, precipitation or flocculation means conversion of colloidal solution into precipitate. So we have colloidal solution. This colloidal solution is converted into precipitate. So conversion of colloidal solution into precipitate is what we call as coagulation or precipitation or flocculation. Now, this coagulation is carried by, this can be achieved by different methods, different means. One of the most important means is we are saying that all these colloidal particles are charged particles. If we neutralize these charges by addition of an oppositely charged electrolyte, then the charges will be neutralized. As the charges are neutralized, the particles will come closer, stick together, will aggregate, and these particles, larger particles, will settle down under the influence of gravity. That is what we call as coagulation. So the methods by which this coagulation can be achieved is by addition of electrolyte. So by addition of electrolyte whose charges is opposite to the charge on the colloidal solution, charges will be neutralized and coagulation takes place. So this is one of the methods. Second is by addition of oppositely charged colloidal solution. Suppose we have a colloidal solution which is negatively charged, so we take another colloidal solution which is positively charged. So both are mixed together, positive negative will neutralize, and both colloidal solution will coagulate. That is known as mutual coagulation. Next, by boiling, we can also this coagulate by boiling. We can also achieve this coagulation by electrophoresis. So during this, as we have discussed, during this electrophoresis, particles of colloidal solution are moving particular towards a particular electrode. As the particles are moving towards the electrode, these are deposited in a particular electrode and this will underneath settle down. So these are the means by which this we can achieve precipitation or coagulation or flocculation of colloidal particles. Now that means if the colloidal particle is positively charged, we require negatively charged ions to neutralize to coagulate. If the colloidal particles are negatively charged, we require electrolyte which is positively charged to coagulate. So based on this, we have a rule which is known as Hardy-Schultz rule. So Hardy-Schultz rule says coagulation of a colloidal solution can be achieved by an electrolyte whose charges is opposite to the charges of colloidal particle. That is electrolyte. Now we are taking electrolyte whose charges is opposite to the charges of colloidal particle. Then this Hardy's rule says the coagulating power of an electrolyte is directly proportional to the valency of the coagulating ion, which is also known as the active ion. So as the valency increases, the coagulating power of the active ion increases. So rule says coagulating power is directly proportional to fourth power of the valency of active ion. Fourth power of the valency of active ion. That means as the valency increases, the coagulating power also increases. That is, suppose we have a negatively charged colloidal solution. For negatively charged colloidal solution, we have to take a positive charge colloidal solution. We have to take a positive charge electrolyte. So as the valency increases, the coagulating power also increases. So look at it. So the coagulating power of aluminum plus 3, we have valency 3 is greater than the coagulating power of magnesium, valency is 2, which is greater than the coagulating power of sodium, which valency is 1. So as the valency increases, coagulating power increases. For negative charge, we are taking cation. For positively charged colloidal solution, we have to take an electrolyte which charges is negative. So for this, FeCN 6 for negative. So valency is for negative, which is greater than phosphate, and valency is 3, which is greater than sulfate, with valency is 2, which is greater than Cl minus, with valency is 1. So as the valency increases, coagulating power of active ions also increases. Now, for this Hardy-Schulz rule, he emphasized on the valency of the ion used for coagulation. He completely disregards the size of the ions. Now, normally what is happening is the ions used for coagulating the colloidal particle polarize the ions of the charges of colloidal particle. So, polarization factor has to be included. So, these can be modified. So, modified Hardy-Schulz rule says we have to take into account the polarizing factor of ion. Coagulating power is proportional to polarizability. Coagulating power is directly proportional to polarizing power of the active ion. As the polarizing power of active ion increases, the coagulating power of the electrolyte also increases. So rather than saying the valency of the active ion, we can say the coagulating power also depends on the polarizing power of the electrolyte. As the polarizing power increases, the coagulating power also increases. So we have a colloidal solution by use of an electrolyte whose charge is opposite to that of colloidal particle. This can be converted into precipitate. So this is also defined in terms of a value which is known as flocculation value or coagulation value. So flocculation value or coagulation value is the minimum concentration expressed in terms of millimoles per liter of the electrolyte required to cause coagulation. So that minimum concentration of electrolyte required for coagulation of a given colloidal solution is known as flocculation value. So definition says it's a minimum concentration. This must be in terms of millimoles per liter, the minimum concentration millimoles per liter required to cause flocculation. So these minimum concentration required to cause flocculation of a colloidal solution is known as flocculation value. So if the minimum concentration required is more, the coagulating power will be less. If the minimum concentration is less, the coagulating power will be more. So when we compare this coagulating power and flocculation value, these are inversely related. So coagulating power of an electrolyte is inversely related to flocculation value. So coagulating power inversely related to flocculation value. If the minimum concentration is large, coagulating power is less. If the minimum concentration is less, coagulating power is more. So this is coagulation or flocculation value. To define the coagulating power of the electrolytes used for conversion of colloidal solution into precipitates. And finally, we have protection of lyophobic salts. Lyophobic salts being unstable, this is normally protected by use of a stable lyophilic salt. So lyophilic salts are used to protect or used to stabilize lyophobic salt. So the strength of the protective power of lyophilic salts, these are measured in terms of a quantity which is known as gold number. So gold number defines the protective